be able to say that the p-value is, say, less than 0.01 or 0.005, or you'd be able to say that it's less than whatever your alpha is. But how would you calculate an exact p-value? What's that? Yeah, the table, or you could do it in MATLAB. Basically, graphically, what we're trying to find there is got your F distribution, so this would be F, numerator, let's look at line 1 here, so it'd be numerator 1, denominator 18, and we're simply trying to find what's the probability of our F value, 9.8, what's the probability of being greater than that? So we're trying to find this area here, and you can either do it via the table by looking up that value and finding the associated alpha. So let me bring up the table here. So this is the F table that you get on the exam, but it doesn't have 18. So let me. So this is an F table that does contain 18 for the denominator here, and this is strictly for alpha equals 0.01. So if we're using the table and we say numerator 1, denominator 18, that's 8.2. So, and we had, what, 9.8, so it's somewhere a little bit more than 0.01. Or no, it's less than 0.01. So you could at least say that. Although, with the F table on the exam, we have these groupings of alpha, so you can look up multiple alphas there. So let's just say for the sake of using this table, our denominator was actually 18. I mean, it was actually 8 instead of 18. And our numerator is still 1. And we had 9, let's say. So 9 would fall in between, say, 0.01 and 0.05, and so you'd be able to say, well, the p-value is somewhere between 0.01 and 0.05, a little bit closer to 0.01. So you'd have a rough estimate of what the p-value would be. Yeah.
So would that mean then that at the 0.05 level, then you can reject the null?
Yeah, precisely. So if we're looking at alpha equals 0.05, you'd be able to reject the null because our 9.8 is greater than this 5.12. But if we're looking at the alpha equals 0.01, we would not be able to reject it. So let's go back to here. So if we were to ask you to calculate these p-values, you could just say, less than 0.05 would be sufficient. Probably not going to ask you to calculate p-values. Yeah, question?
How do you get the degrees of freedom for the interaction?
Let's see, so that's, I think it's just 1 times 2, right? So it's you can just do degrees of freedom for this one times degrees of freedom for this one. Right.
Is that an equation?
Yeah, so it's, you can look at it in the slides if you want the written out equation. Or just use that. So then what's our conclusion here, given these p-values that we have? What can we say about our nulls? We probably had 3 different nulls, right? One for basically each of these lines. What's that? Oh yeah, well yeah, let's say our critical value is 0.05, just by default. Yeah, we can reject which nulls? All of them, right? We can reject all the nulls here. So that would be our conclusion. Again, if you're not given an alpha, just assume 0.05, but we'll be explicit about what your alpha is. Any questions? Yeah.
Does it say that you can reject interaction term, then you can usually reject as well?
Yeah, right. So that gets at that masking that Jen possibly talked about. So if your interaction term is significant, you can automatically assume that each of these terms are significant as well. Even if these p-values were greater than 0.05, it just might basically kind of what's going on there is all the significance is kind of showing up in this interaction term, which means that each of these terms have to be significant as well because they make up that interaction term as well. So, but mathematically, all the significance would say show up in this interaction term and not show up in these individual terms. But because this term is composed of each of these, then those two terms have to be significant, or I should say factors have to be significant. Yeah. Yeah, Thomas.
What are the null hypotheses for these three?
Right, so going back to this. Yeah, we're just saying, all the interactions, the null is that all their interactions are equal to 0, and the alternative is that at least one is non-zero. Not that they're all non-zero, but at least one is non-zero. And the slopes and intercepts. The same thing for slopes and intercepts. So any questions on this 2A notebook? Okay, so let's try another one here. So now suppose we want to see which of the 4 grandparents does a better job of feeding these babies. So for the next 40 meals, we have the 4 grandparents alternate feeding the bottles. So each grandparent feeds each baby 10 times, or feeds both babies 10 times. And then we look at the percentage of food left over. So these means are the mean amount of food left over, right? So we have basically the mean amount of food left over for Grandma 1, Grandpa 1, and Grandma 2 and Grandpa 2. The standard deviations for the first 10 samples, second 10 samples, third 10 samples, and then all the samples for 10, right? So what kind of ANOVA is this? So we're just doing one way here because we just have one factor. So what's our one factor here?
Grandparent.
It's just grandparent, right? And our response is mean food left over. So again, fill out this table. Why don't we just walk through it because you did it for the last one. So it's basically the same thing. Degrees of freedom. What should it be for between the groups? Yeah, 3. And within groups? So we had 40 observations, right? Minus 4 levels. And then our total is some of these things. Sum of squares. Let's see. So how would we tackle filling out these sum of squares? What would be our first step here? Right. How would we do that? Yeah, just divide this by the degrees of freedom, which was 36, right? So divide this by 36. I'm sorry, multiply by 36 to get that. To get this number, and then how would we get the between groups? Subtract, right? So we subtract the number that we get here from the total. Right. So yeah, our first step was 36 times this would give us this value. Then this value that we're given minus what we just computed will give us the sum of squares for the between groups. Then we can compute the mean squared error for between groups by doing what? Divide this 500 divided by 3. Will give us that, and we just need to figure out one f value here, right? Because we really just have one factor, and that's grandparents. How are we getting this f value?
I think 4 by 26.
Yeah. So we're getting that by just dividing this guy by this guy. And again, same thing on getting this p-value. We can look at the f table. So here are, what's going to be our numerator for the f value here? 3 in our denominator, 36. So I have to go to the internet version of the f table here, but let's see, 1, 2, 3 would be the third column here. 36, so we get like about 4.5 would be our threshold at the 0.01 level. And this value is definitely greater than that 4.5. And so we'd be able to say that this p-value is, what inequality could be right there? That it's at least less than 0.01, right? I'm sorry, so I should have said that this table here is at the alpha equals 0.01 level. So it's at least less than that alpha that is associated with that table. And if you had MATLAB handy, you could calculate it's actually 0.00013. So again, what's our conclusion here? Yeah, we can reject the null. So what was our null here? I didn't ask you beforehand, but what's the null that we're rejecting?
That the means are equal.
That the means are all equal, right? So a follow-up question is, so if we've just shown that all the means are not equal, how would we investigate which means are different? What's an efficient way of doing that?
Fisher's?
Yeah, Fisher's LSD, right? So, so actually, let me ask real quickly, what's convenient about this data set that will make Fisher's LSD easy to implement? What's that? Yeah, you have the means and standard deviations right here. That certainly helps. But what also helps out a lot?
And
Ends are all the same.
The ends are all the same, right? And why does that ease the computation burden on you guys? Why does that help out so much?
Factor of 2.
What's that?
Factor of 2.
So it gives you the same denominator for all those Fisher test statistics, right? We're basically doing a pair t-test here. And recall that our standard error is basically our mean square error times 1 divided by n for the first mean plus 1 divided by n for the second mean. In this case, all the n's are the same. So we have 10 no matter which means we're pairing. Either A would be first grandma 1 and B would be grandpa 2. So it would be n1 and n2. So since all the n's are equal to 10, we've got the same denominator when we calculate all these different Fisher test statistics. So it helps to just do this denominator first, and that comes out to 2.3. And then all we need to do is look at the difference in means for all the different pairings of the grandparents, right? So A and B would be grandma 1 versus grandpa 2, and the difference there was 8.5. Divide by this 2.3, and you get 3.96. Our critical T, we're saying, is going to be alpha equals 0.05, and since this is basically a two-tailed test, we're just looking at differences in means. We're not saying one's equal than the other. I mean, one's greater than the other or less than the other. We're just looking for inequalities here. We've got two tails, so we divide by 2. So effectively, this is alpha equals 0.025. And our degrees for freedom here is 36 for the we're just comparing it's 3.69, which is our test statistic calculated from comparing the means here, to our critical value. And so when you compare grandma 1 to grandpa 2, you can reject the null that they're equal. And you can go through and do that for the rest of the parents too. Yeah, question?
Why do you choose the variances of the same?
So basically we're taking this mean square error from the within groups comparison, right? This is what we're saying is essentially our variance. And we can say that's the same because this is applying to all the groups, right? So we're comparing basically this statistic is a summary of comparing the variances of all the groups together. So it's
Because the LSU comes from the pair t-test, right?
yeah, essentially, yeah.
And the pair t-test, you have to consider whether or not the variance is the same.
Right, yeah, and so what we're doing here is basically assuming that they're the same. So it's sort of a modification of that. The Fisher's LSD is sort of a modification of that pair t-test, and it's inherently assuming that this is giving you a pool variance, basically. Does that make sense? Which is nice, it makes it easier. You just take this value and plug it into the square root in your denominator term. And yeah, question?
On the test, if you just take the two closest numbers and find that it's significant, you have to do the test for every combination.
So no, you wouldn't have to do that yet. You could do this smartly and say, yeah, so which one on here is our closest one?
If you just take the smallest difference.
BD, right?
And point out, yeah, 0.1 more significant, you don't have to do the rest.
Yeah, so what he's saying is, if you look at B and D, right, those are the closest, right? So if you look at those two and do the Fisher's LSD for those two, you find that you do not reject. But really you need to find that difference where you do reject, right? That's what we really care about, is rejecting the null. So so you can't just take that closest one and test that because it fails to reject, right? If that closest one did reject, then you know that all the rest reject. But you would have to kind of work your way through. So I guess to make it easier, you could start with that one and then go to the next one, and then until you get the smallest difference in means that gives you rejection, right? Does that make sense? And then you know that any greater difference in means will reject as well. Or you can just test them all. Yeah?
So that the individual standard deviations don't really affect what you calculate it to?
No.
Okay.
Because
Shouldn't it?
Well, so what we're doing is we're assuming that all those individual standard deviations come from a pool. They're all coming from the same population variance, right? That our population of feeding times all share the same variance, and all those different S's that were in that table are just a random sampling of this one true variance that is common for all 4 groups. And so our MSE then gives us a better estimate of that true pooled variance than the individual ones. So we can just use this value. So that's sort of the inherent theory behind Fisher's LSD. But if you didn't make that assumption, if you were just doing kind of individual pair t-tests, just kind of randomly, you didn't use an over before, then you would use those S's and it'd be much more cumbersome. So ultimately we have 2 cases where we get rejection that's between A and C and B and D. And so I think ultimately if we wanted to put this in qualitative terms, we could say that the grandmas are more efficient at feeding than the grandpas. So any questions on Fisher's LSD or ANOVA here? How that all works? Okay, so let's see, is there anything else? So let's talk about dogs. Who here owns a dog? Or has a dog at home? So what's the, everybody says, dog years. What's the quoted ratio of dog years to human years that everybody spits out? 7, right? You just take your age, let's say you're 1 year old, your dog's 7, so you would say your dog who's age 7 is 1 year old, right? Yeah. Wait, what? Oh yeah, right. So if your dog's 1 years old, he's equivalent to a 7-year-old child. Yeah. Okay. However, that's not exactly true. Basically, some dog scientists actually mapped out what true human years map to dog years, and ended up with this data here. So actually, if your dog is 0.17, I think that's like 2 months or something. Your dog's like 2 months old. That's more equivalent to a 1 and 2 month old or 14-month-old child, and so on and so forth. And actually, if you plot these, you get something that's more like this. So we have dog and human. You actually have a higher ratio at the beginning, and then it levels out here. So actually, dogs kind of mature more fastly in their adolescence than humans do. I don't know how the scientists did this mapping. I guess they looked at, like, I don't know, behavior or something like that. And let's see, first thing. Whereas so this is actually the true relationship, and then kind of what's always quoted is that we have just a constant 7 slope here. This is what's kind of assumed, right? So everybody kind of assumes this just linear relationship that that you take human age multiplied by 7 and get dog age, or you can write that dog equals 7 times human. So automatically you can see that we've got this linear model here. But let's see what we actually get if we fit a linear model to this data that these dog scientists have. So let's see. I'm just cutting off the bottom here, which is actually pretty cool. Just bear with me 1 second. Yeah, that's good. So suppose you're given this table here. So this is actually the raw data, and this column is just these values times these values. And we have the y squareds and the x squares. And at the bottom, you're given the sums of all the columns here. So let's say we want to actually fit a line to the real data and figure out kind of what the true general slope should be. The true general ratio of human years to dog years. So why don't you guys work in groups and find out what our least squares estimate of the parameters for this model would be. And I left something out of our model right here. What did I leave out? What's that? The what? Yeah. Or we're just doing a line. So we've got an intercept, right? Plus intercept. Or more generally, what we've seen is y is beta 1 times x plus beta naught. So given this table, let's fit that model to this true dog data. few different ways you can do it. So I'll just show you one way, but I mean, there's all these different ones. Have you guys worked it out? Should we step through it? Or do you want a few more minutes? No answer. What's that?
I would say we can.
Okay, so let's just go ahead and step through this. So you're given this here table, we've got the sums, finally square estimates. So this is the way I would do it. I think this is probably more easier. There's more complicated versions of equations that will give you the same answers. But what I would do is just first calculate the mean of the y, mean of the x, and that's pretty easy to do. You just take those sums and divide by the sample size, which was like 18, right? Or 17? What else? Yeah, n was 17. Then we get our sum of squares for the x's. And so this 1015 just comes from our sum of x squares, which got cut off there. Sorry about that. And we're subtracting n times the mean of x squared, right? X again here is the human years, and y is the dog years. What's our equation for finding these values? What are we plugging in here? Where'd that 6,300 come from?
Some of the xy.
Yeah, this is our sum of x times y, right? So we're just plugging in that sum here, subtracting n times the product of our two means that we just calculated. And that gives our sum of squares for the interaction, x times y. Then it's super easy to get our intercept here, our slope here. This is just our sum of the xy's divided by our sum of squares for the x's, for x squared. So we're just taking the ratio of these two things. We get about 5.46. And we get an intercept there, right? So our intercept we can just find by rearranging our original model, and we plug in the means, plug in the beta 1 that we just got. You should get 7.59. Just a side note, let's a side discussion on practicality here. Would it really make sense to fit a model with an intercept here? Why not? Yeah, because both species start at 0, right? There's no, if humans are 0 years, why should your dog represent, an age of 7 human years? Doesn't really make much sense. So actually, if you fit a model with an intercept of equal to 0, you get a slope that's more equal to 7. But for the sake of this problem, let's just keep on with this. So the more practical approach would be to set this to 0 and solve for that. But we can proceed with what we have here. So then how would you go about finding the sample correlation between these two variables? what information would we start with to begin to calculate our sample correlation? So we can use some values that we just calculated from that previous question. We need to find out one more thing. What would we find out first here to get our sample correlation? Yeah, the sum of squares for y. And once you find that, then it's just a piece of cake. So yeah, sum of squares for y. So here's our sum of our y squares minus n times the mean of y squared. Will give you this value. And then our sample correlation, r here, is just sum of squares for our interaction, x times y, over the square root of sum of squares for x squared and sum of squares for y squared. And you get a pretty high correlation. So this model actually fits really well. I mean, it should, it's in squares, but it's whether or not it's valid for the physics that's going on here is questionable, right? Because we have the interceptor. But anyway, this is a nice and easy way to calculate that sample correlation. So next, if you're given a standard error, so we wouldn't have you guys find a standard error, but given the information in the slide, you could find that. It would just be a bit cumbersome. So you're given that the standard error for the slope, beta 1, is 0.1751. So let's conduct a hypothesis test to see if this slope is significantly different than 7 dog years per human year. So this is a little tricky because, I guess, prior to this question, what have we only asked you about in terms of hypothesis tests for the slope? So let's... So what's the H naught that we've typically seen for beta 1?
0.
Yeah, that it's beta 1 is equal to 0, right? And our alternative is that beta 1 is not equal to 0, right? Except what are we asking here? Yeah, is this different than 7, right? So here we're replacing 0 with 7. Under this initial, what you have seen usually with beta 1 equal to 0, what was our test statistic? It was beta 1 over the standard error for beta 1, right? How can we adjust this to incorporate our new null here? Yeah, just subtract 7 from the numerator, right? So now we're just doing beta 1 minus 7.
Why do you subtract 7?
So I guess the more general form of this is beta 1 minus, so it would be beta 1 hat, let's say this is your estimate, minus the true beta 1 over the standard error for beta 1, right? So this is the more general form of this test statistic, except it's just most of the time, pretty much all the time you're doing hypothesis tests on slopes, you're looking at this guy equal to 0. And the reason for that is you're usually testing if the slope is significant. And it's significant if it's different than 0. If you have a slope of 0, you have no real linear relationship between x and y, and that's what you're really looking for. So you just want to see if that's different than 0 most of the time. However, here we have a reason for testing if the slope is different than 7, right? Because inherently, society assumes that this ratio between human years and dog years is 7. And we want to see if this actual new data suggests that that ratio is different than 7. So we're just changing that around a bit. Another way to think about this is that you could just rewrite this as beta 1 minus 7 is equal to 0, right? If you want to put it in the form of the original hypothesis that we've seen on the slide.
So what's beta 1 hat?
Well, what is beta 1 hat? What's beta 1 hat? Have we found that already?
5.46.
Yeah, was that 5.46? we calculated previously, right? It's that slope that we found with the least squares estimates. What's our standard error? Yeah, this right here, 0.17, given in the problem. So super easy to find this. You just plug in what you previously found, subtract 7, plug in your standard error, and you have a test statistic. Then what do you do with this test statistic? Yeah, you're going to compare it to some critical value. And where do you get that critical value from? From what kind of table? T-table, right?
Why is it a T-table?
It's a T-table because let me think. Because basically you're doing I mean, you can think about these as means. They're kind of like the changing mean over x's. And you're just doing difference of means where you don't know the true variance. So you can think about it that way. Yeah. Or just know that you use the distribution when you're looking at the slope. Yeah.
What sort of test are you doing? So should you do like a two-tail?
Right, yeah, so here we just want to see if it's different than 7, right? That's all we're asking.
So for the two-tail, it just has to be less than
So for the two-tail, let me draw that over here. So for two-tailed, we've got our t-distribution. Actually, let me leave that arrow in the middle. Doesn't help things. Got our t-distribution that looks sort of like a normal distribution, right? And we calculate some test statistic, which comes out to be negative 8.8. So let's say our test statistic here is negative 8. What condition or conditions would lead to rejecting the null hypothesis? So you'd look up in the table and get a critical value of 2.14, right? So our critical value is over here. Critical value equal to 2.14. And we've got 0 here, right? And we're doing two-tailed, right? So what are our conditions for rejecting the null? Yeah. So if it's either our test statistic is over here, or what? Or our test statistic is less than what value?
negative.
Yeah, negative critical value, right? So we have negative 2.14 here. So for two-tailed, you have to look at two tails, right? The upper tail and the lower tail. And our test statistic is less than the negative version of our critical value. So we can reject the null and say what in words? So we can say we're rejecting the null, and if we wanted to talk about, the science that's going on with dogs here and say, make a statement that was meaningful to the public, how would we write that? Yeah, that this ratio of human years to dog years is, the data supports that it's significantly different than 7. Now we have some other ratio that's different than 7, and something on the order of 5 would be more appropriate. Yeah.
So is that only in the case where you have a non-zero intercept?
And yeah, so this is assuming the model that we fit, which was a non-zero intercept, which again we talked about, and you may want to look at the case where you have you set the intercept at 0 instead.
So you could do another hypothesis test for.
Yeah, so you could,
oh,
you could use the more appropriate model given our previous knowledge. But for the sake of this problem, I wanted to use it. If you do it that way, you actually get a slope that's not significantly different than 7. And I wanted to do something that was more interesting. Yeah.
Why is the degrees of freedom 17
Um, right. Yeah, because we've got 2 unknowns in our model, right? We have beta 1 and beta 9, right? So we're using up basically 2 degrees of freedom by finding those. And so you do your sample size minus 2 for that.
Don't know beta not?
No, so we found out what that intercept was, right? When we with the least squares estimate.
Yeah, okay. But are we doing the test just for one of them? Are you gonna use the intercept in the test too? This will affect the
Let me think about that. It comes, well, no, because you use that minus 2 degrees of freedom also permeates into your standard error calculation. And so you have to use the beta naught that you calculated previously to figure out the S. So we can talk more about that. So how do you find this S? It was in the slides. I don't expect you guys to memorize it, but it was square root of 1 over n minus 2, sum of something here. And what was there? In words, not in mathematical notation. Anybody remember? Sum of squared something. So this would be our sum of squared residuals, right? What's the word residual mean? It's basically our error, right? In the y direction, right? So this is our different y's minus, our true y's, so our data y's minus our predicted y's given our model, right? Squared. So this first y is our data. This y hat is what's predicted by the model. So y hat is equal to our beta 1 hat times our x's plus beta naught hat, right? So that's where the beta naught comes into our error there. So we are in fact using that beta. This slide. So long answer to your question. Yeah.
Would it be different for a model with more than 2 coefficients?
Yes. Again, for the same reason, right? Because if you're doing multiple regression, you're going to have more betas in here, right? I don't know if you can actually see this. To calculate your y hats, you've got to incorporate more betas. You've got to use that full model. So you have a multiple regression problem with, say, beta 1, beta 2, beta 3, and a beta naught. You've got 4 betas, so you have to subtract 17 minus what? 4. Right? So, yeah, I mean, this is easy to calculate with a computer. It's a pain in the butt by hand. Because you would have to go through and actually punch in your calculator what all the different y hats are, and then the difference, and square them. So we wouldn't have to actually ask you to calculate this S here, but we may give you, say, the S, and you have to figure out what the standard error is, or we would just give you the standard error. So that was the last example I have. So we can just do Q&A for the remaining 20 minutes. And if you don't want to stick around for that, you can take off if you want. Yeah. No. So we're not going to ask you fractional factorial design. That was really just in the context of the lab and the homework and to expose you guys to it, but what? So I think it would be, given how much time we spent on it, it would be unfair to put it on the exam.
What about modeling poker probabilities?
Modeling poker. So
Right,
from
so
very
like
beginning
setting
of
up
the
the
semester?
choose and the...
Oh yeah, definitely. I mean, that's everything you've learned before ANOVA. I mean, including ANOVA and prior is valid.
Could we review setting it up? Like, for
setting it
example,
up.
like a specific hand, like how we would set up the choose functions.
Right. Yeah. Yeah. Let me
Sure.
rewind a bit mentally here.
Yeah.
So, poker hands.
Do you know what it is?
Those are the questions.
Do you know what it is?
2020 notice.
Just not forward.
2020 wave notice.
What?
2020 wave notice. That's the whole problem.
So poker hand stuff. Let me think. So what's
So say the probability of drawing, or the odds of drawing a two-pair hand.
two pair, right? So we've got two pair. You've got say you've got your 5 cards, right?
Right.
And you've got same number, same but different number. Same but different number, and then any number not equal to previous numbers, right?
Right, right.
I'll look at it.
So for this first category, you've got how many numbers do we have that we can choose from?
13?
13 different numbers, right? So 8 through 10. And so your first card can be any one of those, right? So we're basically choosing 1 out of 13. Then your second card, let me think here. So then your second card has to be the same as that, right? So 1 of 13, and then we've got to do